Hi, my name is Dr. Christina Hedges, and I am going to be talking today about detecting solar system objects in TESS. I'm based at the NASA Ames Research Center, where I'm working with a small group who are all trying to figure out the best ways that we can detect solar system objects using TESS. I'm also contracted by the Bay Area Environmental Research Institute. So we're trying to answer this question, what can we achieve for solar system objects with TESS? TESS is a fantastic instrument. TESS is observing all sky and is really designed to do astrophysics, but TESS can help us in the planetary science community. TESS is a really unique asset. TESS is going to be, for the first 13 sectors, TESS has already observed. TESS observed 50,000 solar system objects at magnitudes of 20 or brighter for a week or more. And remember that TESS is an instrument that has a 30-minute cadence. And so we've gotten precision, high cadence observations of tens of thousands of asteroids using TESS already. And this makes it a really unique asset. Even though that TESS cannot go as faint as some of the ground-based observatories can, TESS can give us really good baseline, and crucially, it can give us this high cadence, good duty cycle observation so that we can get really detailed information about the light curves of these objects. So there are a couple of things that we really care about when we think of what we can do with TESS. And as far as the science that we can do with TESS goes, for solar system objects specifically, we're thinking detection. Okay, so what can we do in terms of detection of known objects? How faint can we go? What sort of speeds can be of asteroids can be detected in TESS? What are the populations of objects, the known objects that we can detect with TESS? And then also detection of new objects. For this talk, I'm mostly going to be focusing on the detection of known objects. It is a possibility to use TESS for detection of new objects. I will say that TESS cannot go as faint as some of the ground-based observatories can. And so really TESS is more of a characterization mission for the planetary science community than it is a detection mission. So when it comes to characterization, we care about light curves. TESS is really great at getting the light curves of these objects. We already have a lot of tools at our disposal to be able to get at the light curves. The data is on this really high cadence, even though it's slightly lower precision than some observations, some other observatories. Using those light curves, we can get at rotation rates. We can get at rotation rates for a really big population of objects. And the crucial thing here is that TESS gives us this uniform data set on these objects. Even if the baseline is between a week and up to a month, there are ways that we can correct out the selection effects for that slightly different baseline. But the key thing here is that we're getting lots and lots of high cadence observations. And so we can get down to really short periods. We have good coverage of long periods. So we get this sort of large overview of rotation rates for these objects. And then long-term variability. TESS can have a significant baseline because TESS returns to some sectors. And because these objects are moving, for some objects, you can actually get 2 sectors of observations separated by roughly a half a year to a year. And so you can look at the sort of long-term trends for these objects. We can also look at astrometry. Now, TESS is not a mission that is designed to do really precision astrometry for asteroids. TESS is got a mission that's got really, really big pixels. And again, it doesn't have a huge amount of precision. And so astrometry really is something that is quite difficult to do with TESS, but I'm going to come to that a little bit later in the talk. And then finally, we might care about population statistics. Like I was saying, TESS has over 50,000 objects in the first 13 sectors that are brighter than 20th magnitude. So we can really start to build this hierarchical model of the population of main belt asteroids using TESS because we have so many of them and they have this quite uniform observation strategy. We also care about what the data looks like, not just about the science. And for TESS, the data has a lot of sky background. This is an additive background. There's a lot of scattered light in TESS, and this really does impede our ability to get at these objects. So there's the scattered light. TESS also has stars in the way of these objects. So there's a lot of moving objects that are moving across the stellar background field. And so that's also an additive noise when we're looking at these objects. Then there are some extended objects in TESS. It's a really broad all-sky survey, so there's lots of things that are in the field of view. There's also motion noise. Motion noise, in this case, is a multiplicative noise source where TESS is slightly shifting during the course of an observation. There's velocity aberration and there's also jitter. And what this does is that it creates a sort of a multiplicative noise as the star field and the asteroids themselves are slowly sort of moving around on the detector. This can be something that can be really large for early campaigns and then a little bit smaller as TESS observations got a bit more stable. But this is a significant noise source. So object motion, TESS jitter. There are other sources of noise, which include the TESS straps. TESS has these stripes in the data set, which are from straps on the back of the detector. I'll show you a little bit more about that in a few moments. The pointing precision is a potential source of noise. The TESS precision is more than good enough to do the astrophysics that we need to get done with TESS, but it's not necessarily as accurate as we necessarily need for astrometry with asteroids, and I'm going to come and talk a little bit more about that too. So on the screen, I'm showing you an example of what TESS data looks like. For anyone who isn't familiar with TESS data, this is just one sector, and this is fantastic. We've got lots of things in here. This is a huge field of view. Lots of objects potentially whizzing around in here for us to extract. Unfortunately, this is what TESS data looks like a lot of the time. TESS data has this huge scattered light in it, and this scattered light is really big compared with the magnitude changes that we would expect from asteroids. And so we really have to get rid of this if we're going to do anything with extracting asteroids. What we can do is we can do a sort of median background subtraction, and that will work in some cases. But you can see on the screen now, if I sort of draw your attention to some of these corner parts here or this part here, you can see that there are these sort of glints and this high spatial frequency noise that's in this data. And this can potentially get in our way if we were to just do a median background subtraction. And so really what we want to do is we want to come up with a model that is going to well fit this scattered light so that we can get at all of the solar system objects that are buried in this data set. So let's take a look at some data. I'm going to show on the screen now a short movie of just a small piece of TESS data. This is sector 2, and this is about a 512 by 512 cutout. In fact, it may actually be 256 by 256 cutout of a piece of that, that sector 2 data. And then what I've done here is I've done a really simple difference imaging, which is to take the median image, and then I've taken it away from all of the frames. I'm going to replay this a few times as we watch it. You can see that this difference image has a lot of structure in it. I've highlighted just a few of the brightest objects in this data set with those rings and those names. So the things that I want to draw your attention to, first off, if I replay the movie from the beginning, you can see that here we have this scattered light, which is really dwarfing all of the other sources of both signal and noise in this data set. You'll see about in a few seconds, there'll be another sort of huge upswelling of scattered light noise. This is something that's really going to get in the way of our characterization of these objects. We're really going to have a hard time getting rid of this. So that's the scattered light noise. That's hard to get rid of. The second thing is these straps. I'll just replay that portion for you. These straps here and here, these are, again, they're pieces of metal that are on the back of the detector, and they're scattering more light back into the pixels, and they can be a real pain as well. We get a lot of objects that are moving over these straps, and we ideally want to get rid of them. The other key source of noise that I want to draw your attention to is these stars in the background. Now I've done this difference imaging, as I've said. I've taken the median image. If I pause here, when I take the median image away, unfortunately, because there's this slight motion in the image, including velocity aberration, we get this this sort of effect where you see there's a brightness on this side of the source and then a darkness on this side of the source. And that's because the images aren't perfectly aligned. And this is a huge source of noise, especially when you consider this is just about as bright as any of the bright asteroids. If you get asteroids transiting over these sources or near to these sources, it's really going to contaminate your flux. It's going to be a huge source of noise. And so this is something that we would ideally like to get rid of. Yeah, you can see also here in the background, you can see these much fainter objects moving around. So even though we care about bright objects, really to get at that sort of 50,000, we're going to have to get much more closer to the noise limit to get some of these fainter objects. So With the help of my team, we've been developing a new tool to help us get rid of this scattered light background in TESS with the purpose of being able to get to a data product that we can actually use for planetary science to be able to get access to these asteroids. So on the left-hand side, I'm showing you, this is sector two again, and this is a full camera CCD readout here, which is about 2000 by 2000 pixels. This is the real data, and the thing that you can really see in this image is there's this significant blurring at the edge where we have this it's actually to do with the lenses of the camera. There's this sort of blurry edge piece because of the round camera down here. And then there's actually a scattered background offset in this image. You can also, if you were to zoom in, you'd see the straps in here as well. What the new tool that we've been developing does is create this model here, which is made up of 3 components that I'll tell you about in just a moment, and then you can see the residuals here of the data minus model. We do a really good job here of getting down to a really close to 0 background removal here. And so this is very, very useful for when we're trying to get access to these planetary science objects, these asteroids, but potentially also really useful for astrophysics. The model that we built to do this is really pretty simple. We create a model which is mostly polynomials, which gives us our sort of first pass at getting this background. And then we have a model for straps, and then this spline model, which helps us get the high spatial frequency noise as well. And what we do is we fit this as a linear model to every frame in the data set, masking out all of the stars using just some basic data statistics. And then we build this, this linear model in a sort of fast way. The really nice thing about this linear model is that once we've built it, it becomes really, really fast for us to then reevaluate this model at any point on the detector. And we can actually package this as a very, very small file. I'm going to show on the screen now. This is what we can do if we are able to use the tool that I've shown you here and some additional corrections using principal component analysis. I'll play that again. This is a similar sized part of the detector. And what you can see is that we've gotten rid of all that star background. We've mostly used principal components for that. And then we've also got rid of the scattered light in this image. You can see that the asteroids are basically all that's remaining. And so this is what we want to get at. This is the data product where we want to be able to now pull out these asteroids and then fit their light curves. So the tool that we've been developing to do this is called TESS Backdrop. This we're trying to develop really standalone tools to do this. So TESS Backdrop is exclusively just to get rid of the scattered light background. It will do something for you to help get rid of the jitter in static cases. And so TESS Backdrop, what it does is it creates these files, which are this model, this linear model, which is the components of polynomials, spline components, and strap components. But crucially, it will also evaluate that for you. If you were to try and use this tool, assuming that you have the driver files, which the tool can make, and which I'm intending to make now and then give to the community as a high-level science product, you can correct TPFs really, really fast. The idea with TESS Backdrop is that if you were to pass in a TPF file, like the one I'm showing here, if you were to pass that into TESS Backdrop and just correct it, you'd be able to get rid of the scattered light in milliseconds in this file. It doesn't depend on where the file was. It doesn't depend on the sector that it was in. So long as you have the driver file, this should be really lightning fast for you to evaluate. And then the idea is that we are now going to be able to create these moving TPFs, which are going to be target pixel files that are put directly on the asteroids, and then we'll be able to correct them too. So this is a tool that's under development at the moment, and this will really help us beat down that scattered light noise. So I'm excited to push this forward. We're in a really early stage right now, but hopefully over the next few months, we'll be getting this tool ready to give to everybody in the community. So now that we've gotten rid of that scattered light, really the next thing that we need to do is to be able to extract the moving objects themselves. So I'm working with a researcher at NASA Ames, Garrett Berenson, and he's been doing some excellent work making all different kinds of tools for this project. One of the tools that he's been making is TESS Cloud. TESS Cloud is a way of getting access to the full frame image data. It actually works on AWS, which makes things slightly faster. And TESS Cloud is able to get access to the moving objects, that is, any of the solar system objects that have been observed in TESS. So I'm showing on the screen now an example of how to get access to that data. You can just import TESS Cloud and then cut out a known asteroid. You can pass in a start time and a stop time, and then you'll get out a target pixel file, which will be very similar to the pixel files that are given by the TESS mission. And that pixel file will be centered on the object of interest. I'm going to show you an example of this now. I've actually shown you Apophis. Apophis was observed in sector 35 of TESS. I believe it's an NEO. And so this is a really interesting object. It moves extremely fast. And then I'm going to show you this moving TPF now. So instead of this TPF being focused on a single star, we're now having Apophis as the object that's been centered in the middle. And then you can see the stars around Apophis moving in the background. You can see that the scattered light, we haven't actually corrected the scattered light in this file. So when the file goes dark, it's because there's a significant amount of scattered light. You also see that there are some red lines. That's where Apophis is actually crossing over a sector boundary or a CCD boundary. You can see that there's plenty of flux here for us to be able to extract this object and potentially get a light curve of it. And so that's what I want to show you now. So please do check out TESS Cloud, which again is a little bit under development, but TESS Cloud will be able to help you get access to the data and extract the objects themselves from the TESS data. If we were to take the data that I've just shown you and we wanted to make a light curve of it, it would look something like this. This is the raw data. If we were to just put a simple aperture down on the Apophis data that I've just shown you, you would end up with a light curve that looked like this. This is what happens if we just sum up all the pixels that Apophis was in at each point in time. The things that you can see include, there's maybe a hint of some sort of rotation rate down here, but there are all these huge outliers whenever the object goes over a star in the background. And then there's this big swoosh here, which is where the scattered light is really large in this particular sector. Of course, we can do a lot better here. We can just remove a lot of the stars, and we can do that with a simple median subtraction. I'm going to show you that now. This is what happens if you do a pretty simple median subtraction to get rid of the starlight in the images. There is a little bit of cruft here where we were very close to that scattered light part. But you can see this is a really cleaned up our rotation rate here. Now I want you to sort of keep this in mind because I'm going to come back to this. I'm going to come back to this in a little moment. But we have these great tools where we're able to get rid of the background, and we're able to cut these images out. As I said, these are under development, but I'm hoping that we're going to be releasing some of these tools for everybody soon. So I also said we were going to talk a little bit about astrometry, and I've been working a lot with Jeff Smith at NASA Ames, who's been focusing on how precise we can get, how accurately we can get the centroids of moving objects in TESS. I'm showing you a movie on the screen now. This is a centroiding tool, which is creating an adaptive aperture for an object. This, I believe, is not Apophis. This is a different object, but it's a very faint object in sector 10. The centroid is the black spot in the middle. Jeff has been working on looking at how close the astrometry would get from TESS is to what we know a priori from the, for example, JPL Horizons database. On the screen now, I'm showing at the top, this is the JPL Horizons expected astrometry for this object, and then the measured astrometry that we get with the centroiding tools that we are developing. You can see on the bottom, the residuals. We're getting really, really close to zero, which is excellent. This is what is expected. We're currently improving the accuracy of these tools, and we are hoping to get this down to exactly zero for all of the objects that we're looking at. We are hunting down just one last reason that this is not exactly at zero. But we're really excited about this, and this is going to mean that we're much better able to take the JPL expected locations of these objects and potentially create apertures using what we know from TESS to just automatically extract the light curves of these objects. The other part of this is the precision. And so, we care about being close to where JPL says that the asteroid should be, but then we also care about understanding for all of the times that TESS is observed, where is that object? We care about the precision of all of the observations, all of the cadences in a single observation. And so I've been working with Rob Morris, who's at NASA Ames, who's been focusing on this question of precision. And what Rob has been doing has been creating PSF photometry for these moving objects. This is really exciting work, and Rob's been using the TESS information, the information on the point spread function of the TESS instrument, and been using that information to build PSFs of moving objects, and then using that to fit their light curves. What Rob then gets is both the centroids of those objects, which is very exciting. I'm showing those on the screen now. You can see this is the column and row of Apophis. You can see that they are pretty close to zero. This is, in this case, we forced that. The thing I want to draw your attention to is the fact that this is very narrow in arc seconds. TESS pixels are 21 arc seconds across, and you can see that with a standard deviation of approximately 0.25 arc seconds, that's the level to which Rob is able to get precision astrometry for Apophis, which is really exciting. So we're working on a publication now about how to do this PSF photometry with TESS and how to get this really good astrometry. The second thing that Rob gets for free is the flux of these objects. And so I'm showing that on the screen now. This is analogous to that orange light curve that I was showing before, but this has become much cleaner. In this case, we got rid of the data that was close to that significant scattered light, but this is an incredibly tight light curve. The noise properties of this are greatly reduced, and you can really see this rotation rate for Apophis. We're very excited about this technique, and we're planning to put out a publication about the light curve of this object very, very soon. So one of the questions that I wanted to answer with this talk is, well, what's the limit with TESS? What's the limit that we can do planetary science and look at solar system objects with TESS? So I'm showing on the screen now an object. This object is about 19th magnitude in TESS. What I've done is I've summed up the object in a moving TPF. And so I've taken every single cadence in a moving TPF around this object, and then I've stacked them up. And when you add them up, you basically then get a sort of detection of this object. On the left-hand side, I'm showing the light curve of this object. It looks pretty ratty, but when you do a periodogram of this object, you see that there's actually a really significant period over here at 1.7 hours. And then this is the light curve that's been folded on that period. And so you can see that at 19th magnitude, we're absolutely doing really valuable light curve analysis here. This is only 5 days worth of observation, and there are easily tens of thousands of objects that are at this level in TESS. So we're definitely going to be able to get at interesting rotation periods, even for faint objects. I think the faintest that we're probably going to be able to go is roughly around 22. This was the object that was the most faint that I could possibly pull out some sort of interesting rotation period. This does depend a little bit on the amplitude of the rotation periods that we find with TESS, but this was the faintest that reasonably I could go is about 22nd magnitude, where I could potentially pull out an interesting light curve and see a significant detection. It may be with PSF tools we could beat this down further. So as I've said, the TESS data provides this really unique opportunity for the planetary science community. And the thing that we're really trying to do in my group at Ames is we're trying to get really good tools so that TESS users and the planetary science community can get at this data. There's obviously a wealth of it down to a ridiculously faint magnitude. But our heritage is really working with astrophysics missions, and I think there's a lot that the astrophysics community can do to help the planetary science community. In particular, we have a lot of tools that can help in this very special, unique case that TESS can help us see. Because TESS has this long, well, relatively long baseline and really high cadence, we can get at light curves like the ones I'm showing on the screen. The ones on the top are light curves of two different objects. Their names are in the top here. And these are not our final light curves. These are very preliminary, but I wanted to show you them because you can see something really cool and unusual, which is that these objects are binary objects. You can see over here that there are these eclipses that are happening very periodically in these objects. Now, these objects are known binaries. The one over here you can see has this really, really steep phase curve variation here. These are known binaries, and TESS is able to see that they are these eclipsing binary asteroids, and they have really exciting light curves. What we'd like to continue to work on is taking some of the astrophysics tools that we have, including tools for finding transiting planets. Those are really relevant in cases like this. Tools for modeling eclipsing binaries, really relevant because they're super analogous. And by understanding the properties of these binary asteroids that have these eclipses, we'd like to be able to get at more information about the hyperparameters of the objects in these binaries. And so one of the things that we're pushing forward to work on is how we can take the astrophysics tools of BLS and transit fitting, transit modeling, eclipse modeling, and apply them to cases like this to try and find binary asteroids. So there's lots more exciting tools to come. All of our tools are publicly online. They're all available on GitHub. Please come check them out, leave us issues, and please feel free to email me if you have any questions. As I've said, we're hoping to get these tools out over the next few months, and we've got some papers in the works that we're really excited to share with the community. Thanks very much.